Hey guys, welcome to another video on my channel. This video is going to be part of my engineering statics series. In this video, we will discuss some introductory concepts and cover some essential review material. This material is only intended to help you do well in your engineering college courses and not meant as a replacement. Many of the definitions and concepts in this video will be based on the R.C. Hibbeler Engineering Mechanics Statics 12th edition book. Without further ado, let's get started. These are the topics that we'll cover in this video. First, we'll talk about scalars and vectors. Then we will look at Newton's 3 laws of motion, which are vital to understanding engineering statics. Then we will look at a general introduction to statics to give you an idea of what we study in statics. Rigid bodies are very important in solving statics problems, so we'll go over what is meant by a rigid body. After that, we will look at some trig review. A scalar is any positive or negative physical quantity that only has a magnitude. Length, mass, temperature, and time are examples of scalars. The length of a table is 12 feet, for example. There's no direction for that. Temperature can be either positive or negative, but there's not a direction for temperature. On the other hand, a vector has both a magnitude and direction. You need to specify both direction and magnitude to fully describe the vector. For example, let's say you're applying a 100 Newton force to a box. Well, if I don't know which direction you're applying the force, I don't know how the box is moving. The box could be going this way, or if you're applying the force in the y direction, it could be moving this way. Or if you're applying the force here, the box could be moving in the negative x direction. And let's say you asked your friend to come help you and push, and let's just say that you are pushing in the positive x direction. Now you asked him to help you push the box, but you don't specify the direction you want him to push. If he's pushing in the opposite direction, then that's not doing you any good. Your forces may very well cancel out and the box may not be going anywhere. That's why it's very important to be giving both direction and magnitude for a vector. Vector is graphically represented by an arrow where the length of the arrow represents the magnitude of the vector. A vector with a larger magnitude should be shown with a longer arrow. For example, if we have a 10 Newton force, then a 100 Newton force vector should be relatively longer. Vector has the magnitude, but it also has sense. Sense is another way of saying the vector's direction. The line on which the arrow lies, this dashed red line, is called the line of action. The angle between the vector and a fixed axis, such as the x-axis or the y-axis, defines the angle of the line of action. Let's start with Newton's first law. Newton's first law of motion states that an object at rest will remain at rest and an object in motion will maintain a constant velocity unless acted upon by a net external force. A couple things to decipher here. First of all, this doesn't mean that the object does not feel any forces. The key word here is net. the forces simply are balanced. This object right here that has three forces acting on it, but the object is at rest. In order for the object to be at rest, the net external force must be zero. So what do we mean? Let's say that this is our positive x direction, and this is our positive y direction. Then the force, then in order for this object to be in equilibrium, meaning no net forces, all the forces in the x direction must sum to zero, and all the forces in the y direction must sum to zero. So what forces do we have in the x direction? Well, F1 is pointing down and to the right. So this has an x component that is pointing to the right. So there's an x component of the F1 force. And similarly, F2 is pointing down and to the left. So there's an x component of F2. So given that the x direction is taken to be positive when it's pointing to the right, and we know that the forces must sum to zero in order for this body to be in equilibrium, we have F1x, and to that we're going to add the x component of F2, but we know that it's pointing to the left and thus negative, so we'll subtract whatever the magnitude of F2x is, and we can say that in order for this body to be in equilibrium, F1x must equal F2x. And now we have to look at the y direction, because the y components of the forces must also be equal to zero. The net force must be zero. So what forces do we have in the y direction? Well, once again, we have F1, which is also pointing down, and F2, which is also pointing down. But F3 is pointing up. So we have F1, y, F2, y. In order for this body to be to experience a net force of zero in the y direction, we need F1 y, which is pointing down, and this is going to be negative, minus F2 y, whatever the value is, that's also negative because it's pointing down, but we're going to add F3 because that's pointing in the positive y direction, and that's all going to sum to zero. In other words, F3 must equal F1y plus F2y. When this condition is met, that the y components of F1 and F2 equal F3, and the x components of F1 and F2 are equal, then this body will be in equilibrium. If it's at rest, it will remain at rest, and if it's moving, it's going to keep moving at a constant velocity because there will be no net or unbalanced force acting on it. And as we look at more problems in the future, it will start making more sense. But keep in mind that the first law doesn't mean that there's no forces on the body. It just means that the forces are balanced and there's no net external force or unbalanced force. Let's continue looking at Newton's first law a little bit more. Pretend that the yellow rectangle represents your engineering statics book resting on a table. You put the book down when you got tired of doing your statics homework. When you come back from taking your little break, the book is still there, fortunately or unfortunately. The book was at rest when you left to take your break, and it remained at rest the entire time. It wasn't that the book wasn't experiencing any forces, but all the forces in all directions were balanced. The book's weight exerted on the table due to gravity is pointing downwards, but the table also exerts a normal force that points upward and is equal in magnitude to the book's weight. The forces in the y direction are balanced. There are no forces in the x direction. Therefore, the book experiences a net external force of 0, and it will remain at rest. So when you come back from your break, you can continue your homework. Now let's look at Newton's second law. According to Newton's second law, an object acted upon by an unbalanced force F, or a net external force, experiences an acceleration A in the same direction and a magnitude that is directly proportional to the force. Let's say we have this box. You're pulling on this box in this direction, and your little brother or nephew is pulling on it in the other direction. You're much stronger than he is, and you're exerting a larger force on the box than the little guy. Therefore, the net external force on the box is pointing towards you. Whatever that net external force is causing an acceleration of the box, and that acceleration is proportional to the force that the box is feeling. Another thing to notice in this equation is that if you have a larger mass, for the same force applied on the object, you're going to have a lower acceleration value. For example, let's say we have 100 newtons of force applied on a 2 kilogram object. So that's the mass, 2 kilograms. And then we have the acceleration. We're just going to look at the magnitude now. We're going to ignore the direction. So let's just look at the magnitude. So if you have the 100 newtons, and let's divide that by 2 kilograms. And remember, 1 newton is equal to 1 kilogram times meter per second squared. So when we divide both sides by 2 kilograms, we will get that the value of the acceleration is equal to 50 meters per second squared. On the other hand, if we have the same force, 100 newtons, but we have a more massive object, let's say we have a 50 kilogram object, what will happen to the acceleration? It's going to be much smaller. Let's divide both sides by 50 kilograms, and your acceleration value will only be 2 meters per second squared. If it's a heavy box, it will accelerate slowly. If it's a lighter box, it will accelerate much quickly. Statics, the net external force will be 0, and therefore the acceleration will be 0. So the forces will always be balanced in statics. We won't have an acceleration. Newton's third law, the mutual forces of action and reaction between two particles are equal in magnitude, opposite in direction, and the forces are collinear. And let's take a look at objects A and B. Let's say if object A exerts a force on object B, then object B also exerts a force on object A that is equal in magnitude, opposite in direction, and collinear meaning on the same line of action. And this blue dashed line is representing the line of action. We'll look at all of that when we look into vectors a little bit more. And one more thing that is important to remember is that the two forces are acting on two different objects. Force of A on B, on is the keyword here, is the force that B feels. The force of B on A is the force that A feels. And that is Newton's third law. Having looked at Newton's third law, let's get into engineering statics. What do we study in engineering statics? Statics studies equilibrium of bodies that are either at rest or moving at a constant velocity. The net force on the body is equal to 0. In other words, having looked at Newton's laws, but the body has no acceleration because the net force is 0, and thus the acceleration is 0. The forces will always be balanced, and therefore the body will not be accelerating. Dynamics, on the other hand, is concerned with accelerated motion of bodies, and that's typically studied in a different course. We'll look at statics in this video series. When we solve statics problems, we'll need to use the rigid body assumption. This is an idealization of a body that does not deform or change shape. The body can be seen as a collection of particles where the distance between particles remains constant. Let's take figure 1 as an example. Let's say this is a wooden block and we're going to call out 3 particles on this block: particle A, particle B, and particle C. As this wooden block has load applied to it, the distance between A and B, B and C, and A and C do not change under the rigid body assumption. Whether there's a load or whether it's not feeling any load, before and after feeling loads, this body will not be deformed. And statics will assume that all bodies are rigid bodies. This eliminates the need to take material properties into account. In reality, bodies aren't completely rigid. However, deformations are typically relatively small, which means the rigid body assumption can be used reasonably in these statics problems. Now let's start with some basic trigonometry review. It's important to remember that the interior angles of a triangle sum to 180 degrees. This may seem very basic, but it's very important for everything that we're going to do with trigonometry. And complementary angles sum to 90 degrees. So let's say this angle is 45 degrees. So then, since this angle is complementary, this must be 90 minus 45 degrees. In other words, this angle right here is also 45 degrees. Similarly, supplementary angles sum to 180 degrees. A straight line is 180 degrees. So if we have this angle, which is it's an acute angle less than 90 degrees, if we say this is 30 degrees, then this bigger angle right here must be 180 degrees minus 30 degrees, which is 150 degrees. Vertical angles are congruent, meaning they are the same angle value. So if this is theta, then this is also theta. And if two lines are parallel and there's a line intersecting them, if we overlaid this parallel line over here, we would come out with the same scenario, meaning this angle will also be theta this angle will also be theta. If you just pictured moving this line right above this line, you see that you have the same scenario, theta, theta, and then this angle right here, we'll call that phi, must be 180 degrees minus theta because they are supplementary. And then this angle here must also be phi because they're vertical, and also this is supplementary. Same deal up here. If this is phi, the vertical angle will also be phi. So let's say, for example, this is, once again, let's say 30 degrees. Then opposite angle is also, the vertical angle is also 30 degrees. And then this angle must be 180 minus 30. In other words, 150 degrees. And this angle is also 150 degrees, 30 degrees, 150 here. The theta here is 30 and 150. And you can see that this also satisfies the supplementary angles rule. When we have a right triangle, we can use a special theorem known as the Pythagorean theorem. Let's say C is the right angle, which is 90 degrees. We know that interior angles of a triangle sum to 180 degrees. So in other words, angle A plus angle B plus angle C must equal 180 degrees. If angle C is 90 degrees, then angle A plus angle B must equal 90 degrees, meaning that both A and B are smaller angles than 90 degrees. Triangle, the longest side is opposite the largest angle. Therefore, side C, which is opposite the right angle, is going to be the longest side. This is called the hypotenuse of the right triangle. Sides A and B are called legs of the triangle. According to the Pythagorean theorem, the length of A squared plus the length of B squared equals the length of C squared. Another way of saying it, A squared plus B squared equals C squared. Let's look at if we had a theta. Let's say we have an angle theta right here. Then the opposite side to that angle would be, the opposite side to this angle would be A. So let's just write OPP for opposite. That's a terrible P. Let's try that again. Let's write OPP for opposite, and then ADJ for adjacent, and this is still the hypotenuse. The sine theta of this triangle is opposite over hypotenuse. So in other words, it will be A over C, and the cosine theta will be adjacent over the hypotenuse, so that will be B over C, and tangent theta will be opposite over adjacent, so that's A over B. If my theta, instead of being here, was over here, let's do that in a different color. Let's say we'll do that in blue. Let's say I have a theta here. Then now, what's opposite that angle? The opposite side is now B, and hypotenuse is still C. The adjacent side is A, and the opposite side is C. Opposite is B, and then adjacent is A. That's for the tangent. Quick way to remember this is and many of you may be familiar with this, SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. That's it for this video. I hope you found this video helpful in some way. If you haven't already, please subscribe. Check out other videos on my channel, especially the MATLAB tutorial series, as well as the calculator series, and check out the calculus videos. I hope you guys are staying safe and healthy. Until next time, take care, guys.